I thank the organizers for arranging this conference and giving me the opportunity to participate in it. I'll be talking about phenomenology of dark energy. So let's start off by understanding exactly what phenomenology is. It means to appear, to manifest, but it also means to illuminate and to bring to light. Literally, it means that which is perceived by eye. And so we have data, we perceive characteristics of the data, properties of the data, through the eye, and then ideally, that then maps onto from phenomena to noumena, that which is perceived by the mind. That is, we go from observations to the phenomenal properties of the data to a theory. So ideally, these three things should work very closely together, going from observations, phenomenology, and theory. Sometimes it doesn't work well together, and there's a famous instance from the 1800s, what I call the Battle Royal, where two of the astronomers royal, one the Astronomer Royal of England, Airy, and one Astronomer Royal of Ireland, Hamilton, were debating an optical phenomenon, and the experiment was done, and Hamilton was right, and Airy said, I should not have believed it had I not seen it with my own eyes. And Hamilton says, how different we are. I should not have believed it had I not proved it. So that's somewhat of a difference between the sort of phenomenology and the theory aspects of it. But nowadays, hopefully, we work more closely together and not quite as much in conflict with each other. Hamilton's a really interesting person. He was actually appointed Astronomer Royal when he was an undergraduate. So that's pretty amazing. And there's a hilarious parody in the style of the Broadway Hamilton show from Acapella Science. And I list the YouTube link to that below if you want to learn more about his life. So what is the phenomenology of dark energy? So currently, what the data is telling us is that when we combine together the baryon acoustic oscillation data from DESI, the cosmic microwave background data from CMB experiments, and supernova data from various compilations, that we do not lie on the cosmological constant. The best fit to the data does not lie on the cosmological constant in the crosshairs, where the value today of the equation of state W naught is not -1, and the time variation quantity WA is not 0, but we lie significantly off from that. We bring all these different types of data together, and they are very consistent in what each one tells us. And this has really moved on since even a year ago, and that now the updated supernova compilations, the recalibrated supernova compilations, are in extremely good agreement with each other. Before, they were still in good agreement, but now they're in extremely good agreement with each other. And so it doesn't look like the phenomenology of dark energy is agreeing with a cosmological constant lambda. It doesn't seem like it agrees with the thawing class of dark energy that I'll talk about very shortly, which is what we were basically expecting if you go back, 2 years or more. But it lies in what 2 years ago we would have thought was an impossible place. And so this is very exciting, very interesting, and we've got to figure out how did the impossible become possible? What leads to this phenomenology? So let's review what the standard law of dark energy is. So I have this quip, dark energy does not exist in a vacuum. So what this means is that dark energy, whether it's vacuum energy or something else, actually lives in a universe which was in the early times dominated by radiation and matter, and it evolved for many, many e-folds of the expansion. And so we cannot consider dark energy all by itself, but we have to take into account that long history. So, in particular, what that long history of radiation and matter domination does is it gives a very rapid expansion, which can be viewed as a high Hubble friction from the expansion. And so that's going to tend to lock any evolution of the dark energy in place. It is thought of as a friction. It really prevents the dark energy from moving. But there's also a driving term, which you can think of as an effective potential, the steepness of that potential. And that's the force which does want it to move. And so you've got these two forces contending with each other. And so you have generically sort of two outcomes. Dark energy will either be frozen initially, the friction wins out initially, but then as the universe expands, the Hubble friction decreases, it may then thaw and move away from the frozen state, away from the cosmological constant state. On the other hand, maybe the effective potential, the driving force, is large enough, is steep enough that the field rolls initially, but again, eventually it must come to a shallower part of the potential. It must freeze. That is, it moves toward a cosmological constant lambda. So a couple of years ago, we basically thought those should be the two possibilities for how dark energy should behave. And they define fairly narrow regions in a phase space. So we can define phase space in terms of the dark energy equation of state W, the pressure to energy density ratio of the dark energy, and its time variation, W prime. So that's a phase space, just like position and momentum, X and X dot are a phase space. And so those two forces, the Hubble friction and the driving of the steep potential, as I said, either leads you in the thawing region, moving away from a cosmological constant, so this blue triangle in the upper part of the diagram, or initially you were rolling and then you slow down and you freeze toward a cosmological constant, which again is at W of -1, W prime of 0. So 2 years and more ago, we really would have thought that one of those two blue regions was where dark energy data would end up. And in fact, data was already sort of mitigating against the freezing region. And we really thought that it would end up either in thawing or at the cosmological constant. So why did we think all the other regions were physically disfavored? Well, let's first look at the middle region. So we had these two forces. The middle region is such that the two forces are essentially exactly in balance, not just at a single moment, but over long periods of the universe. So that seemed like an unnatural fine-tuning. And so we did not think that the middle region, a constant W with no W prime, we did not think that very, very likely at all. How about this high region? The high region you can show actually violates that principle of dark energy does not exist in a vacuum, that dark energy lived for many, many E-folds in a universe that was dominated at early times by radiation and matter domination, which we really thought, that's a pretty bedrock principle of cosmology, early radiation and matter domination. So the high region we thought was ruled out. The low region is one where the field is actually rolling upslope, opposite the way you would think things should go. And we knew that there were theories like K-essence that could do that, but we thought it pretty unlikely. And again, the data was sort of disfavoring this whole lower part of the phase space. And then, of course, there's the whole left-hand side, the phantom region, where W was more negative than -1. And again, we knew ways to do that, but they were not very standard ways. And so we tended to go with the simpler theories, which would have been the thawing or the freezing. And in particular, earlier data was leading us toward either the thawing or the cosmological constant. So that's why we disfavored these other regions. Okay, what then happened? Well, the first thing is we can't actually fit the full phase space diagram. We can't fit those two free functions, W of A and W prime of A. It's like knowing the position and the momentum of a particle at all times. The data is simply not good enough to do that. And already 20 years ago, it was shown that instead of two free functions for the dark energy equation of state, you really are able to only fit two numbers, two quantities, two parameters to describe the equation of state. And that is because the data as it exists currently, is sometimes called stage 4 dark energy data, dark energy survey data, is only good enough to do two numbers out of that. And that can be shown and was shown 20 years ago fairly generally. So now we have to get our functions, our phase space, shown here on the left side, down into somehow numbers. So again, here are the thawing and the freezing regions that I showed before in the blue hatch. Now they're the yellow triangles. And again, we see that they actually do limit the phase space. They are fairly narrow triangles. The dark energy can't just be anywhere according to that principle of either Hubble friction dominates or the steepness of the potential dominates. And here you can see some exact scalar field theories. Again, this is from 20 years ago, and that the exact solutions all lie in these triangular regions, the exact solutions of the Klein-Gordon equations, either the thawing region or the freezing region, where the endpoints of all these curves is today. And so to try to condense this phase space into two numbers, we can choose, for example, what is the value today? What is W at the endpoint of whichever curve, whichever theory you're talking about? For the time variation number, it doesn't do any good to choose that value to be today, because then instead of a curve, all you've done is you've chosen one point on each curve. And that's not giving you enough information. So instead, what you want to do is you want to stretch the time axis. You want to take the W value at the endpoint, but then you want to stretch the time, which stretches W prime, the logarithmic derivative with respect to scale factor, in such a way to calibrate these thawing and these freezing relations. And so let's take those two numbers where we've done a stretching of the time and we've taken the value today. We'll call those suggestively W0 and WA as calibrating properties. And we find that's extremely successful, that this whole thawing triangle becomes this very, very narrow triangle, almost a straight line in this new phase space of W0, WA, when we've stretched the time, when we've calibrated. And the freezing theories sort of separate into different narrow bands or almost lines within the freezing class, depending on what they were doing basically back in the higher redshift universe. So we end up with this calibration of taking these reasonably narrow regions of phase space and making them into extremely narrow regions of phase space. And that, again, is coming all from the physics. These curves are exact solutions of the scalar field equations. And now we've condensed it to two numbers, which is capturing those essential properties. That's what you want phenomenology to do. And that is the meaning of the W0 WA relation that we use. It has a ridiculously simple form. And we're just fortunate that we can capture the universe in a simple form. But we did not start with the simple form. We started with the exact solutions. We started with the time recalibration. Anyone who says this looks like a Taylor expansion has just never read the original papers from 20 years ago. Okay, there is physics behind it. There is calibration behind it. It is a physics-based encapsulation of these free functions, full functions. And that is what phenomenology is meant to do. Okay, so now let's take the data from 2026 and ask, what does it look like if we adopt not lambda CDM, which would just be this horizontal dashed line, but we adopt this W0 WA CDM. And we find that the data gives us this orange band with several very strange properties. It's lower than -1 at higher redshifts. It's less negative than -1 at lower redshifts, which of course means that it's crossing -1. Instead of a dark energy equation of state, you might want to think a little bit more globally in terms of the deceleration parameter of the universe, Q of Z, and that's shown here. Again, the dashed line is what you get in lambda CDM. And again, we're seeing that what the data is saying is that you actually are more accelerating, less positive, more negative Q at these intermediate redshifts between redshift zero point 0.5 and 1.5, say, but you are less accelerating more toward the positive regime at recent times for redshifts less than zero point 0.5. So even though I've told you that for 20 years, W naught WA has worked extremely well at capturing the physics of the exact solutions of the scalar field equations. This is such a strange result that you might very rightfully say, well, let's make sure that it's not a peculiarity somehow of W naught WA. And so let's ask what happens if we don't use W naught WA. And in particular, we can do various functional form independent ways of analyzing the data. So the blue shows a Gaussian process method where there is no functional form assumed for W of A. And both the blue on the right, the left side, W of Z, and on the left side, the right side now, the deceleration parameter are the Gaussian process results. So there's no functional form assumed. We see it's very consistent with what we got from W naught WA. DESI went to great lengths to test many different form independent ways. For example, independent redshift bins, where each bin in redshift can float independently as it likes. We did those bins in equation of state of dark energy, and we did those bins in density of dark energy. We also did orthogonal polynomial expansions. All of those give that same sort of result where you start in the phantom regime at these high redshifts, you cross what's called the phantom divide, W equals -1, and today the phenomenology is that W is less negative than -1, heading upward basically. Okay, so this looks pretty robust. The data really seem to be telling us this. So I call this beautifully bizarre. So let's put into words the properties that we just saw. Okay, again, this phantomness, this rapid evolution, crossing -1, and going upwards from -1. And so that's these four properties that I've just written down here. In particular, that rapid evolution is actually faster than what we would have thought Hubble friction would allow. And so it seems to say there's some extra push going on with the field. We need to add some physics to give it that rapid evolution, as well as we need to give it some extra physics to enable it to cross W of -1. And then we have this fact that it's sort of changing nature along the way in that it's evolving away. It doesn't stop at -1 at cosmological constant, but it evolves further away from it to less negative W0. So actually in the 20-year time span that I've been talking about, we knew the physics to do each piece. There was literature on how to do each piece, but they never went together. The physics was different in how you got each piece that the phenomenology is pointing to from the data. I do want to mention this footnote, this phantom divide crossing W of -1. Robert Caldwell and I made very clear that this is not null energy condition violation. Null energy condition's a completely separate thing. Our universe has never violated the null energy condition, and it does not look like it ever will violate the null energy condition, even though it has crossed W of -1. So please take a look at that to get that straight. So this is beautifully bizarre. So now the role of phenomenology is to point us toward some theories. Before we do that, let's mention that the data shows us one other strange aspect phenomenologically. When you analyze within lambda CDM, the current data says that the sum of neutrino masses is negative. So here you can see what the posteriors are from different data combinations, that they all lie in this gray shaded regime where the sum of the neutrino masses is negative. That's clearly a very strange thing. It's a bizarre thing. I would not call it a beautifully bizarre thing. So we want to understand what's going on there. And it turns out that dark energy can tell us a bit about what's going on there. When we, instead of lambda CDM, we analyze within W0, WA CDM, now we see the posteriors have all shifted so that a substantial part of the posteriors lie in the positive regime. And these vertical dashed lines show us the normal minimum normal hierarchy and minimum inverted hierarchy numbers. So you can see that both of them are allowed by these posteriors when we analyze within the W0 WA CDM. And so is the dark energy telling us something about the neutrino mass, or is the neutrino mass telling us something about the types of dark energy that we need? Let's look into that a little bit more. So one of the things is going from lambda CDM to W0 WA CDM, you've added two parameters. So the first thing you might ask is it just a parameter space volume effect, some sort of degeneracy? And you can remove that possibility by going from two parameters at least down to one parameter model. Maybe it's the property that the dark energy has the rapid evolution, that phenomenology. Does that push the neutrino mass negative or positive? What about the phantom crossing phenomenology? Or what about the fact that at high Z it's phantom? So we wanted to sort of zero in on what the actual answer is. And so here we've shown the neutrino mass as a function of six different one-parameter dark energy models. So there's the thawing model that we already know about, more generalized thawing models, which have a very rapid evolution, point number two. Um, and then you've got this sort of pink-purple region, which is a mirage model, which has the phantom crossing and it's phantom at high Z, but it's still a one-parameter model. And we see that that is successful. It's as successful as the W0 WA model was. So we don't need two parameters. One parameter dark energy is sufficient. So it doesn't seem like number one is the right answer. From the fact that the generalized thawers don't work, it doesn't seem like number two is the right answer. We can take a phantom model, the so-called Gede model, and we can see that, well, that moves the posteriors, the contours up a little bit, so they were a little bit positive in the right direction, but not quite well enough as well as the mirage does. And so what that is indicating is it's moving in the right direction. So the fact that it's phantom at high Z seems to have some influence. And it turns out that that is indeed the required property to move the neutrino mass to be positive. But what you also need is you need that phantom crossing, which Gede does not have, to get you a good fit to the data. This article, Yang Di Valentino and Zhang and Pan, is out. I just did not put the complete archive there, but you can look at it under these authors. And again, this should actually be the required property in order to get the neutrino mass to be positive is the phantom dark energy. Okay, let's go back to this phenomenology, this beautifully bizarre phenomenology. How can we use these four different properties to give us a guideline, at least, for what theory should work? So again, it used to be we knew the physics to do each piece, but they would be different pieces, basically different parts of physics for each piece. So now let's see if we can come up with something that makes the pieces a little bit more go together. And so we're testing the framework. So a lot of phenomenology is you're working within a framework, and the phenomenology tests the framework. So not a specific theory, but something more general, the framework. So I like to phrase this as, is dark energy an elephant or a chimera? So you know the old legend about the scientists go into a dark room where there's an animal, and each one feels a different part of the animal. One feels the trunk and says, oh, the animal is a snake. One feels the legs and says it's a tree trunk. One feels the side and says, no, it's a wall. But they're all feeling a unified animal. So these different properties belong to a unified phenomenology, a unified theory, in fact. On the other hand, there's mythological animals, such as a chimera, which are indeed very disparate, very different animals. You have the head of a lion, you have the tail of a snake, you have a goat's head growing out of the back. You have things which just don't seem to go together. You need each separate piece. And so, our question for testing the physics framework, how do we get those four properties that the data points us to, those four phenomenological properties? Is it from a unified framework, an elephant, or is it from many different aspects of physics that aren't necessarily tightly tied together, a chimera? So, what I mean by that, a unified origin, the elephant, could be you have interactions between different sectors, for example, matter and dark energy. You could be modifying gravity beyond general relativity, and you have a unified theory for that. Or you've done something to the vacuum structure itself. Remember, dark energy we're talking about as a vacuum energy. For example, a phase transition. Again, leading to you to a unified theory to explain that. On the other hand, you might go down the disparate origin route, the chimera route, where you say, no, there's many different dark energy fields, and each one is doing their own thing. And that the property of one is to be phantom, the property of another is to cross the phantom divide, the property of the other is to have a rapid revolution, and so on and so forth. Or you can have what Robert Scherer gave the wonderful nomenclature to of fake phantoms, where you have different components, you have dark energy and you have other components, but you've misassigned part of the other component to the dark energy. So, for example, maybe you didn't understand how dark matter behaved. It's not interacting with the dark energy at all. It's just dark matter is not behaving the way you thought dark matter was behaving. And you're going to take that misbehavior and assign it to the dark energy piece. And so the two parts, dark energy and the dark matter, they're not connected. So they are a chimera, not an elephant. They're not unified to give you the phenomenology. So we want to test the framing. The first step is we want to sort of see, can we come up with a unified origin, or do we need many, many different elements which are not so tightly connected together? We also want to use more observations. We want to, of course, do cross checks on the data, different ways of measuring distances, for example, baryon acoustic oscillations versus supernovae. We want to measure cosmic structure growth versus the cosmic expansion. We want to measure the effects of gravity on the growth of matter structures versus lensing propagation, light propagation. And we're getting to the state where we can test the gravitational effects on gravitational waves themselves, in particular, the effect on the propagation of gravitational waves, where there's a friction beyond Hubble friction due to the properties of gravity deviating from general relativity. And we would see that in gravitational waves from black holes and neutron stars. So we want to bring all of that together to test the framework. So let's first look at the first elephant, interactions. So again, we saw that crossing W of -1 was not a property of the functional form that we adopted. It was there in bins, it was there in orthogonal polynomials, it was there in Gaussian processes. It's not an illusion, but maybe you can make something cross W of -1 through a dark sector interaction. So I've written this very generally here, where I haven't specified what function Q is, only that there is a Q and that you are conserving overall the energy momentum tensor. That will shift the equation of state of dark energy, but it necessarily shifts the equation of state of whatever you've coupled it to, for example, dark matter. What that lets you do is take something that's purely phantom and uplift it, so now it crosses W of -1, or you take some dark energy that's purely quintessential, always above -1, and you depress it. So again, it can cross W of -1. But remember, even though you solved how to cross W of -1 through this interaction, you've also changed the matter sector. You've changed its equation of state, And generically, that gives you problems in large-scale structure growth and in the cosmic microwave background. And so it's not to say it's impossible, but it gives you problems that you have to face up to. You could also try tilting dark energy. So you're uplifting in one part and you're depressing in another part to hope that maybe that means that you're not changing the matter equation of state quite as much. It's very, very difficult to do that with a particle physics theory, but it's relatively easy to do that in modified gravity. It comes from this conformal factor coupling to the Ricci scalar, and that conformal factor in Horndeski is called the G4 function. And what you're basically doing is you're changing how the Planck mass runs. Sometimes it runs faster than, sometimes it runs positively, sometimes it runs negatively, and that gives you this tilt. Does that help enough? We don't really know yet. It's not automatically. You really have to go through the calculations of the perturbations of the matter growth to say, does your theory actually work, even though you've changed that matter coupling? The same situation applies with decay. If I make decay, dark energy decay to dark matter, or dark matter decay to dark energy, you get that same issue. Anytime you have an interaction with matter, it's problematic for large scale structure, problematic for the CMB. Again, it doesn't mean it's impossible, but it means you have to explicitly do the calculations. You can't just propose your theory. You've got to actually see what does your theory mean for those data, not just for the distance data. Okay, the second thing you can do is modify gravity. So again, people have tried to modify gravity for a very, very long time. Um, and about a dozen years ago, people started doing pretty simple things where they took their modified gravity and they said, well, let's make it proportional to the dark energy density, or let's make it power law in the scale factor. And very shortly after, a dozen years ago, it was shown that that was a very, very bad thing to do. So here's some examples from more than 10 years ago. We're taking this proportionality. Here it's the proportionality of the Planck mass running, the so-called alpha m parameter, saying that's proportional to dark energy density. Compare it to the exact solution. This does not look like a constant curve to me. Okay, there's a strong time variation. It is not proportional. By the way, this is f of r gravity. So the simplest gravity, the first gravity you'd write down, this is not good for. You could go to more complicated gravities. So this is like a Birchinger-Zucchian type of gravity where you have a sort of Pade approximation for how the effective coupling works. And you take this power law. Again, you get extremely biased results and extremely prior dependent results. It just does not work. Okay. We've known that for 10 years. You should never use that in a paper. What we know does work wonderfully is avoid functional forms and instead work functional model independently. Use bins in the effective coupling of matter and of light for lensing. That we've known again for almost 10 years works wonderfully. Sub% accuracy, here you can see how well it works. We compared it, the binned solution versus exact solutions from an exact theory of gravity. We, in fact, tested over a half dozen exact theories of gravity, very different classes of gravity, and they all work at this wonderful 0.3% level. So again, take a look at this paper, convince yourself bins are the way to go, and look at these papers because how you choose the bins, the number of bins you choose, and how you choose them in redshift and in scale factor are important. And it's been worked out how to do it correctly. So do take a look at those. Okay, now let's again try to use phenomenology as a guide to push us toward a specific theory. So let's say we've done our bins in G effective, that points us in a certain direction. What's our next step? How do we get to a specific theory? So as I mentioned back during interactions, non-minimally coupling the gravity directly to the matter can be problematic. Again, it's not impossible, but it's something that you have to work out with great care. Personally, I prefer to avoid that because it is so problematic. If you avoid that changing the direct coupling to matter, then that leaves you in Horndeski gravity with basically two terms in the action, a kinetic term and a modified gravity term called G3. Okay? Remember, the non-minimal coupling to matter was called G4. K is sometimes called G2. Okay, so those are the two terms that you're left with if you avoid G4. You still have to say what are the functions of these as a function of the field and its derivatives. You might say, well, can we simplify things by using a shift symmetric theory? Shift symmetric theories are great, give you lots of quantum protection, all sorts of great properties. The answer, unfortunately, is no. A purely shift symmetric theory cannot cross the phantom divide. It needs a push. So you have to add a potential to those two terms. The potential actually is implicit in this kinetic term K. It's naturally there. Shift symmetry got rid of it, but what this is saying is no, you can't completely get rid of it. But you can do something which is almost shift symmetric, and you try a very simple linear potential. We know that that has its own quantum protections to go with it. So that's sort of a very natural thing to try. And we can solve the equations numerically, and we find, look at that, it does work. It's phantom at high redshift. The push from the linear potential brings it across the phantom divide, and it becomes less negative. It's heading upwards as you get toward today. And so such a theory, reasonably straightforward, simple modified gravity theory, without any G4 term, and with sort of the maximally simple potential, does indeed work. And you can work out exactly what the equation of state of the effective dark energy is. We've chosen a particularly simple form, which is constant at -2 in the past. The potential pushes it across -1. And in fact, in the far future, it will go to W of +1, which means not only does the dark energy fade away as the matter becomes dominant again in the future, but you actually restore back to general relativity in the future. And so all of your alpha parameters were 0 in the past, 0 in the future. They deviate today, but maybe they don't deviate so far that they're a problem. So this is work with Rodrigo Calderon, and it is in preparation, so I don't have final results to show, but in proof of principle does exist for it. And then the third type of elephant that I talked about was a phase transition. It turns out that there's a very old, more than 20-year-old theory that gives you phantom dark energy. So Leonard Parker and collaborators wrote a series of papers that were very, very interesting. So Leonard Parker literally wrote the first textbook on quantum field theory and curved space-time. So he knew his quantum field theory. And he managed this non-perturbative summation of all the quantum effects on the action. So the Einstein-Hilbert action is simply R. It's just linear in R. But all the quantum effects give you corrections to that. And what he found is you could sum them up, get a finite result, and you got a phase transition. So just like in phase transitions, you have an order parameter where the Ricci scalar R is acting as that order parameter. So it's somewhat similar to condensed matter physics, actually. Very interesting. When that Ricci scalar, through the expansion of the universe, lowers to, it hits the scalaron mass, the scalaron, this is basically a scalar tensor field theory. When it hits that, that's when the phase transition clicks on. What happens after that is a very interesting property that we know about from electromagnetism. You have Lenz's law, which freezes the order parameter. It freezes that Ricci scalar to be a constant value. Specifically, that means it's giving you cosmic acceleration with phantom dark energy. So that's what Parker and collaborators did 20 years and more ago. They gave us phantom dark energy, they gave us cosmic acceleration. But as we know, the current data says you don't have purely phantom dark energy. You have got to cross the phantom divide at some point and go to W less negative than -1. So Robert Caldwell had the very bright idea of after this phase transition, maybe your scalar field decays You've left your false vacuum, and now maybe your scalar field will decay into light scalars. So you're not affecting matter at all. Dark energy is decaying into dark energy. It's just decaying into a different um, property of dark energy. And what you get when you go through the equations, the numerical solution you get, this is due to Kushal Lodha and Robert Caldwell, Eleanor Di Valentino. This is in preparation still, but these are the numerical solutions that we currently have. You see that at high redshift, you were simply in your false vacuum state. It's not exactly a cosmological constant. It is a false vacuum with a different value than you would get it from lambda CDM. You then get a phase transition at a particular redshift. You're in the phantom regime, and now your decay is turning you around, letting you cross the phantom divide. And today you've got a W that is less negative than -1 due to this dark energy decaying into dark energy. When we compare that to current data, to DESI, BAO, to CMB data, and to supernovae, we actually fit the data as well as the W0, WA, CDM does. But now we have a theory behind it to some extent. It has the same number of parameters, this vacuum metamorphosis theory, as W0, WA. It also has a nice property that the fit that you get out is that the decay rate should be very natural. It should be of order the Hubble parameter at that transition. So this is a way that phenomenology points you in a promising direction for theory. The theory is not completely done, not completely evaluated, but it's pointing you in an interesting direction to pursue. So I hope I've shown you that it's okay to have elephants in the room. Chimeras, are more problematic because they're less predictive. If you just have many, many different scalar fields without any relation to each other, well, I mean, you can do almost anything. Whereas an elephant says, no, there's a unifying explanation behind the different phenomenological properties. And so what we're doing is we're taking the phenomena that we see in the data and we're pointing ourselves toward the noumena, toward a theory. So specifically, what I've talked to is the fact that we think that it is physical to have a positive neutrino mass. The way that we get that phenomenologically is that we need phantom dark energy. We need a crossing of the phantom divide. And that will give us then a good probability that neutrino mass is positive as we physically think it should be. Modified gravity phenomenology, again, we know ways of doing it properly in a functional form free way. Binning works wonderfully. Please use it. If you want a specific theory, then we've seen that the G4 Horndeski theories can be problematic. Again, I'm not saying you should never think about them, but I'm saying if you're going to think about them, you've got to think them all the way through. You can't just use them to fit distance data. You've got to look at their effects on matter structure growth and lensing. But a fairly simple modified gravity with just the kinetic term and the modified gravity term and the simplest sort of potential you can write down, no matter coupling, almost shift symmetric, seems to get you across the phantom divide, seems to have the properties, if not necessarily the exact parameters, that we need from the data. And then going back to a much older idea with a nice, strong quantum field theory basis to it, a phase transition in the vacuum seems like it's working pretty well and that it's fitting the data pretty well. Again, it may not be the exactly right theory, but the phenomenon are pointing us toward theories that can work. So to sum up, cosmic acceleration has been fascinating and it's still fascinating us. We still don't know what it is, but it's wonderful ideas that we keep coming up with, and we come up with wonderful data to fit those ideas. We understand the good part of the basics of dark energy, the idea that you have Hubble friction, you've got steepness of the potential, those are your two main forces, and then if you enlarge the physics framework, you have other forces that enter in, and you've got to use those to fit your phenomenology. The universe certainly threw us surprises, we're starting to get our feet under us again and starting to figure out, okay, how do we fit those four different phenomenological properties together in a coherent way? We're testing the framework itself of physics. So it's not about fitting numbers, fitting parameters. It's about understanding what framework of physics we should be working on. From that, that guides us to a theory. And then eventually, maybe we end up with a theory with specific numbers in it. But again, I'd be very happy to understand what framework of physics we're supposed to be working in. Do we have an elephant, a unified theory, or do we have a chimera where there are a lot of arbitrary, seemingly arbitrary properties to it? On the data side, we want to continue to always look at our data with lots of cross checks, BAO versus supernova versus eventually gravitational wave distances. We want to look at distances versus growth of structure. We want to look at growth of structure versus gravitational lensing. And then again, once we have gravitational waves, look at that gravitational friction aspect. We continue to get more and more data. This is so wonderful. Within the next year, we're going to have new data on large-scale structure. The DESI DR2 growth results will be out by the end of the year, we expect. New CMB data and new supernova data. So thank you very much for listening, and I'm really looking forward to the discussions that go on from here.